This small board is what controls my entire rocket. It decides when to deploy parachutes, tracks altitude in real time, and logs all the flight data. And I built it myself, and today I'm going to break down exactly how it works. At a high level, a flight computer is just the brain of a rocket. It reads sensor data, figures out what phase of flight the rocket is in, and then triggers events, like parachute deployment, at the right time. In my case, this one handles altitude detection, flight state tracking, Pyro channel control, and data logging. Furthermore, it will be used in the future for active control and potentially a propulsive landing using solid rocket motors. So let's have an overview of this computer. Before jumping straight into components, here's the architecture. So we have some sensors here, such as the IMU, the barometer, the GPS, which feed data into the microcontroller, which then uses it to process this data and control outputs such as these Pyro channels on the side, which use MOSFETs, and it also stores data in the flash. So first, let's look at the microcontroller, or the core of the system. This is the STM32 H-series chip, which is a bit overkill for a flight controller, but that's kind of the point. It runs fast and has a ton of peripherals and has room for expansion in the future. This chip is responsible for the IMU over SPI, the barometer, which is also over SPI, some other sensors, which are actually pulse coherent radars, which are currently not used in the flight computer, but will be used in future projects for Doppler velocity estimation. It also triggers outputs with precise timing, such as pyros or servo outputs as seen on the sides here. Now let's look at the sensors. The main sensor here is a ICM42688P, if I'm right, which is IMU. There was actually supposed to be dual IMUs on the board, this one and a BN085, but because of inavailability of stock, I have not been able to get my hands on the BN085 yet, but in the future I plan to use that, or maybe a more simplified version, because the main selling point of this IMU is its sensor fusion, which I actually don't plan to use as I'm running my own Kalman filter or unscented Kalman filter in the future. Now this here is the barometric air pressure sensor. Essentially what it does is it converts air pressure into altitude, which lets the flight computer detect liftoff, apogee, descent. The IMU here basically looks at orientation and in the form of quaternions, which can describe rotations and smoothly interpolate between different states. These two sensors combine to help me detect the apogee of the flight, which is the highest point, and detect different phases such as liftoff, burnout, coast, and descent. Now these here are the Pyro channels, which are probably the most important part of the system for a passive rocket, which deploys a parachute to land. They control the deployment of parachutes using small igniters. So actually in the next revision of the board, instead of using two plated through hose, I'll be using a terminal block to better connect the E-matches for firing black powder charges, which essentially deploy the parachute. Now you can see there's probably some damage here, and this actually came while I was soldering because there was a short between two resistors here, which I had to remove, and thankfully it did not impact the system because I actually am not using this IMU right now. As you can see, it's not soldered on. Now let's look at the power system. So this flight computer actually does not have any buck converters yet. It has a header on the top, which is a JST XH connector, which is used to connect to 3.3 volts, 1.8 volts, VBAT, and 5 volts for like these different power rails are supplied by a separate power distribution board, which kind of separates, I would say, the power noise from the sensors. Also, you can see that there's a big pad here, and this is actually for a LoRa module or long range radio. This module was ND at the time of designing, and I did not consider that, so I've not been able to get my hands on it, but I have moved to a more newer module for my next revision of the flight computer, which should help with communication and real-time uplink. this here is a LDO, which just takes voltage 5 volts from the USB and converts it into 3.3 volts, which is usable by all the sensors in the middle here. This here is the GPS. This is actually just a standard GNSS module, so no fancy RTK or anything, but it should be more than enough for first flights, and it's pretty precise, and I'm pretty sure it goes up to 1 meter accuracy in most cases. The most important part is actually the flash. Without flight data, there's no point of flying, I would say, and it's really difficult to improve. I'm logging all flight data so I can analyze performance after recovery. This includes stuff like altitude over time, flight events, and sensor readings. This is how I improve each launch. Now, this process the designing of the flight computer hasn't been very smooth, as it's also been my first or second time making such a complex PCB. Especially these BGA packages down the bottom for the mmWave radars were pretty difficult to root, but I probably won't end up using this flight computer much anyway. It actually flew on board, it was supposed to fly on board a rocket last week, but unfortunately the launch failed due to an on-pad KATO. It was able to fly on another rocket in a passive manner, so it did not directly control servo outputs for active control, but it was mainly just used for data logging, which is still pretty useful for looking at my attitude estimation algorithms. But this is just the first revision, and there's a lot I want to improve in the second version. I'm working on integrated power delivery via 3 synchronous buck converters for 3 different power rails, more robust design and redundancy via a secondary IMU, cleaner PCB layout, a more aesthetic design, and interfacing with the Compute Module 5 for more advanced control algorithms such as model predictive control. Now, this PCB was designed in EasyEDA and sponsored via the OSHW Lab Stars project, and I'll be releasing a full design as open source hardware, so you can check it out, modify it, or build your own. I would like to thank EasyEDA for sponsoring this project. If you're interested in that or want to follow the next revision and flight tests in the future, consider subscribing and leaving a like.